I drink your milkshake.
You are listening to the Billionaire Podcast Network.
Moving my bones, no place to rest. Travel the north just to find my head. I'm still corn-fed. Corn-fed. Moving my bones, no place to rest. Travel the north just to find my head. I'm still corn-fed.
Go. The quantum theory of atomic polarization 1. Polarization by uniform field by R.A. Buckingham, B.A., Queen's University, Belfast. Communicated by J.E. Leonard Jones, F.R.S. Received 29 December 1936. 1. Introduction. That was a microphone picked that one. I don't have the screen that stops it from popping like that. 1. Introduction. 2 problems of atomic energy. The energy of polarization of an atom in a plane electrostatic field and the energy of interaction or van der Waals energy of 2 distant atoms are particularly suited to attack by approximate methods. In each, the disturbing field, whether that of the static field or of the distant atom, is small in comparison with the internal fields acting on the electrons of the atomic system, and so the standard methods by which quantum mechanics deal with small disturbances, namely the perturbation and variation methods, can be and have been successfully applied to these problems. Though the perturbation method, strictly applied, is the more accurate since it takes into account the possible excited states of the system, its usefulness is restricted to atoms of simple structure and having relatively simple wave functions. Generally speaking, the variation methods, which require a knowledge of the unperturbed state of the system only, are more suitable for larger atoms. Ignorance of the excited states is largely compensated for by expressing the perturbed wave functions in terms of parameters, which are then chosen to make the total energy a minimum. As one would expect, the atoms of hydrogen and helium have been studied most fully, the perturbation theory being used by Wang, Eichenschitz, and London and Leonard Jones, and variation methods by Atanasoff, Hasse, Slater, and Kirkwood, Pauling, and Beach. Owing to the first-order Stark effect, the calculated polarizability of the hydrogen atom cannot be compared with experiment, but the calculated value for helium agrees well in most cases with that observed. The van der Waals energy of 2 hydrogen atoms given by Pauling and Beach includes accurate values not only of the usual dipole-dipole term, which varies as 1/r to the 6th, but also of the dipole-quadrupole and quadrupole-quadrupole terms, varying as 1/r to the 8th and 1/r to the 10th, respectively. The most accurate calculation of the dipole-dipole term for 2 helium atoms is probably that of Hasse, 1930-1931, and the higher order terms have been estimated by Margenau, 1931. The treatment of larger atoms has been largely devoted to obtaining a relation between the dipole-dipole constant C, the van der Waals energy being C/r to the 6th, and the polarizability. I don't know what that symbol is. It's like a half figure 8. Theta? I think it's a theta. It was started by London, 1930, who deduced that for two similar atoms, C equals constant I theta squared, or I is the ionization potential. The use of the variation method by Slater and Kirkwood, 1939, suggested that C equals constant in theta. I don't know what that is. 3/2? Where N is the number of electrons in the outer shell, and though their work was restricted mainly to hydrogenic wave functions and functions without nodes, the method was later modified by Kirkwood, 1932, to include any type of wave function. A different line of approach was followed by Venti, 1932, who used the Kuhnreich sum rule to simplify the second order terms of the perturbation theory. The first order terms vanish in these problems, showing at the same time the assumptions made were... Oh wait, I missed a footnote. What does that mean? There was something with a cross next to it, and then the cross says... Oh, Pauling and Beach. For the treatment of H. Wang, 1927, Eichenschitz in London, 1930, Leonard Jones, 1930, Pauling and Beach, 1935, for H. in Hasse, 1930, 1931, Slater, I don't know what the... Okay, irrelevant. Showing at the time that the assumptions made were implied also in Kirkwood's variation method. Using the same idea, Hellman, 1935, was able to extend the results of Venti and Kirkwood by treating the electrons of each atom not as a single group, but as a number of shells, which in the variation method corresponds to the use of several parameters instead of one, and by including the Pauli principle. In this paper, Kirkwood's variation method is used throughout, with one or more parameters and with inclusion of electron exchange and formulae derived for the polarizability of atoms with any number of electrons. The results are somewhat more general than those of Hellman. Calculations are then made with the available wave functions of the rare gas atoms and alkali ions, and the results compared with experiment as far as possible. In a second paper, the van der Waals energy of atoms will be considered. 2. Energy of perturbation. We shall begin by deriving an expression for the increase in energy of an atom containing N electrons when subject to a small perturbing field. We shall assume that the electronic system is in a non-degenerate state, which can be adequately represented by a wave function involving the space and spin coordinates of the electrons only. Thus, if the unperturbed wave function is... This is some Greek shit again. I think it's psi. Looks like a pitchfork. Thus, if the unperturbed wave function is... I'm just going to go ahead and say psi, and its complex conjugate is psi to the asterisk, psi to some... I don't know what this means. The energy of the system is given by E equals... Oh my god, I don't know what I'm looking at. It's like E equals the hole on a violin, psi asterisk H psi dr slash the violin hole psi asterisk psi d dt d theta, where H equals N over sigma, P equals 1 bracket dash 1/2 upside down triangle 2/p plus V, with the P in the lower right close bracket, Vp being the potential energy of the pth electron, expressed as a function of the space coordinates of the pth electron only, and upside down triangle 2/p the Laplacian operator for the same electron. The integration is carried out over the coordinate space of every electron. When an external field is applied to the system, let us suppose Vp to be increased by a small amount, Vp to Vp plus Vp. H is therefore increased to H plus V, where V equals sigma Vp. And at the same time, the function psi is changed to psi plus... Okay, so I think this is a theta. No, wait. Phi? Psi plus phi. Yes. Psi plus phi, where phi times phi is of the order of magnitude v squared. The energy of the perturbed state is then E plus H equals violin whole parentheses psi asterisk plus phi asterisk close parentheses H plus V per close parentheses psi plus phi close parentheses D T over violin whole parentheses psi asterisk plus phi asterisk close parentheses psi plus phi close parentheses dt. H being the energy of perturbation we wish to evaluate. Now, in the problems to be discussed later, V and psi times phi are odd functions. Oh, there's another footnote. The sign of the function is changed if the coordinates of any electron are reversed in sign. Odd functions of the electron coordinates and a number of integrals in the table from 2-2 vanish, including violin whole psi times v psi dt, violin whole phi times v phi dt, violin whole psi times phi dt, violin whole psi phi times psi dt. Hence, E plus H equals 1 over A plus B, bracket, violin whole parentheses psi times phi plus phi times psi close parentheses VDT plus violin whole parentheses psi. No, wait, that's not a multiple. It's like psi to the power, and it's just an asterisk. Psi asterisk plus phi asterisk close parentheses H parentheses psi plus phi close parentheses DT close bracket. And that's table 2-3, where A equals violin whole psi asterisk psi dt, B equals violin whole phi asterisk phi dt. By transforming the integral containing upside down triangle 2 over 2p, upside down triangle 2 over p by Green's theorem, so that the surface integral vanishes over the infinite boundary, and by neglecting terms in v to the fourth and higher powers of v, and also terms of the form a violin whole phi asterisk v p phi dt dash b violin whole psi asterisk v little p psi dt, that's table 2-4, we find that lowercase h equals 1 over a violin whole parentheses psi asterisk phi plus phi asterisk psi close parentheses vdt plus 1 over 2a sigma over p bracket violin whole grad little p phi asterisk grad little p phi dt minus b over a violin whole grad little p psi asterisk grad little p psi dt close bracket, and that's table 2.5. The expression for little h, lowercase h, given by Kirkwood and Hellman is slightly different from table 2.5, but follows immediately from it when psi is replaced by, or when phi is replaced by psi u, little u. That's probably some other, God. Psi lowercase u, provided that we can neglect terms of the type violin whole grad little p psi asterisk grad little p to the u to the 2 psi dt minus 1 over a violin whole psi asterisk u to the 2 psi dt violin whole grad little p psi asterisk grad little p psi dt, that's table 2.6. We then obtain lowercase h equals 1 over a's violin whole psi asterisk bracket 2uv plus 1 over 2 sigma over p parentheses grad little p to the u to the 2, close parentheses, close bracket, psi dt. That's table 2.7. Both tables 2.5 and 2.7 will be used in the applications which follow, and we shall assume that the terms of which tables 2.4 and 2.6 are typical are small in comparison with the other terms of the order v to the 2. And there's a footnote here. Typical or small. It can be shown that when psi is real and satisfies the Schrodinger equation for the atom exactly, Kirkwood's result, table 2.7, holds without approximation. This suggests that when phi cannot be written in the form psi u, the neglect of the terms corresponding to 2.4 and 2.6 is in fact justified. It is intended to examine these terms in a later paper. 3. Polarization by a uniform field. The results of... What the fuck is this? It's like two S's on top of each other? The results of double S2 will first be applied to the increase in energy of an atom in a uniform plane electrostatic field. Let us assume that the wave function of the atom when the electrostatic field is absent is the determinant. Psi equals, and this is a matrix, so it's a big matrix, psi theta 1, psi theta 2, dot, 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 psi theta n, psi... I don't know what this... It's like a bee with some stank on it. It's like a bee with a tail. Psi b1, psi b2, dot, 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 psi bn. And then here at the bottom, psi p1, psi v2, dot, 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 psi double n, closed matrix. That's table 3.1. Where psi theta p and psi bp, dot, 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 psi vp are the wave functions of the occupied electronic states of the atom. The Greek suffix being an abbreviation for the four quantum numbers NLMS of the state, and the italic suffix indicating the electron whose coordinates are inserted. The psi's are assumed to include the spin function as a factor, to be orthogonal, and each to be normalized to unity. If psi asterisk is the conjugate complex of psi, then A equals violin whole psi asterisk psi dt equals n exclamation point. If the integration is carried out over the coordinate space of every electron, psi also satisfies the Pauli exclusion principle and permits any pair of electrons to exchange places freely. When the atom is subjected to an external field, the psi's are changed. It is convenient to express the perturbed function corresponding to psi pp, which contains the coordinates of the pth electron in the form psi pp parentheses 1 plus f parentheses r little p close parentheses vp close parentheses, where v little p is the increase in the potential energy of the pth electron, and f parentheses rp close parentheses is a polynomial function of its radial coordinate. As a first approximation, we shall take f parentheses rp parentheses equals lambda, a constant for all values of p and p. The perturbed wave function of the whole atom is then obtained by replacing psi pp in the determinant psi by psi pp parentheses 1 plus lambda vp close parentheses, and therefore if only linear terms in vp are retained, it is psi parentheses 1 plus lambda v close parentheses, where v equals sigma vp. This function is likewise anti-symmetrical in the electron coordinates and so satisfies the Pauli principle. The energy of perturbation is now given by table 2.7, inserting A equals n exclamation point, U equals psi v, no, U equals lambda v. We have lowercase h equals 1 over n exclamation point violin whole psi asterisk bracket 2 lambda v over 2 lambda v squared plus 1 over 2 lambda squared e sigma over p parentheses grad PV parentheses squared close bracket psi dt. That's table 3.2. Let RP be the position vector of the pth electron and F a constant vector representing the electrostatic field. Then in atomic units, the field perturbing the pth electron is Vp equals dash F dot RP, and so V equals dash N over sigma over P equals 1 parentheses V dot R little p close parentheses dot. That's table 3.3. With the expression for V, table 3.2 can easily be reduced to a sum of simple integrals involving one electron wave functions only. As this part of the process is long, it is omitted here, though further details of this and similar reductions which arise later will be found in an appendix. We find that after averaging for all orientations of the atom relative to the direction of the external field, lowercase h equals f squared parentheses 2 over 3 lambda r squared plus 1 over 2 n lambda squared close parentheses, table 3.4, where r squared equals sigma over p parentheses r squared close parentheses p, and parentheses r squared parentheses little p equals parentheses lowercase r squared close parentheses pp minus sigma over, oh shit, I don't know what this is. It's like an O with a squiggly attached at the top of it. Squiggly O not equal to lowercase p bracket parentheses x close parentheses squiggly O p parentheses x close parentheses p squiggly O plus parentheses y close parentheses squiggly O p parentheses y close parentheses p squiggly O plus parentheses z close parentheses squiggly O p parentheses z close parentheses p squiggly O close bracket. The quantity r squared parentheses r squared close parentheses pp is the average value of r squared with respect to the charge density psi asterisk over p psi p, i.e. parentheses lowercase r squared close parentheses pp equals violin whole psi asterisk over little p r squared psi p dt. It is independent of the electron considered, and so the electronic suffix is omitted. The other terms in parentheses uppercase r squared close parentheses p are exchange integrals, of which parentheses x close parentheses squiggly o p equals violin whole psi asterisk over squiggly o x psi little p dt is typical. These integrals are discussed in detail in SS3A. We see that expression table 3.4 for lowercase h contains the unknown parameter lambda, which must be chosen to make the energy a minimum. Accordingly, we introduce the condition d lowercase h slash d lambda equals 0, which gives lambda equals dash 2 uppercase r squared slash 3n, and lowercase h min equals dash 2f squared 2 over 9 f squared over n parentheses uppercase r squared close parentheses squared. The quantity of practical importance is the atomic polarizability theta, defined by h min equals dash 1 over 2 theta f squared, and therefore given by theta equals 4 over 9n parentheses uppercase r squared close parentheses squared. That's table 3.5 in atomic units. In deriving table 3.5, it was assumed that each wave function psi pp is perturbed in the same degree determined by the parameter lambda. This is unlikely to be accurate, if only because electrons in the inner shells are shielded by those in the outer from a perturbing field acting from without, and so we will consider the effect of using a different parameter for each electronic wave function. Thus, let us now assume the perturbed form of psi pp to be psi pp parentheses 1 plus lambda pvp close parentheses, where psi p is a different constant for each state p from theta to v. The perturbed wave function of the atom obtained by replacing psi pp in psi table 3.1 by psi pp parentheses 1 plus lambda pvp close parentheses now becomes, when only linear terms in vp are retained, psi plus phi. where phi equals sigma over p, lambda p, sigma over p, psi pp, dpp, vp, dpp, being the first minor of psi pp in the determinant psi. Phi is no longer a simple multiple of psi, and so equation 2.5 for the energy of perturbation must be used instead of equation 2.7. However, this does not affect the accuracy of the final result, as in the course of reduction to simple integrals, we neglect certain terms comparable with table 2.6. After averaging for all orientations of the atom as before, we obtain in place of table 3.4 lowercase h equals f squared psi over sigma over p bracket 2 over 3 lambda p parentheses r squared parentheses p plus 1 over 2 lambda 2 over p close bracket. That's table 3.6. And when the parameters are chosen to make h a minimum, h min equals dash 2 over 9 f squared sigma over p parentheses r squared parentheses 2 over p, and theta equals 4 over 9 sigma over p parentheses r squared close parentheses 2 over p. That's table 3.7, where the summation for p includes all the occupied electronic states. Oh, here's a footnote. By applying the Kuhn-Reich sum rule to the second order terms of the perturbation theory, Hellman 1935 obtains the following expressions for theta. Theta equals 4 sigma over I, parentheses z squared, close parentheses II, bracket, parentheses z squared, parentheses II dash, sigma over k, not equal to I, matrix, parentheses z, parentheses ik, matrix squared, close bracket. As, different orientations of the atom relative to the external field are not considered. When written in the same way, table 3.7 becomes theta equals 4 sigma over I, bracket z squared, bracket parentheses z squared, parentheses II dash sigma over k not equal to I, matrix parentheses z, close parentheses ik, matrix squared, bracket squared. It is not clear why the two results should differ. And then we're back. Okay, that's the footnote. And then, okay. As a further refinement, we shall take the perturbed form of psi pp to be... What does this mean? Oh, it's another footnote. In dealing with Hasse, 1930 showed that for the introduction of the linear term of the polynomial f, parentheses rp, parentheses, improved the calculated value of the polarizability considerably. The higher powers of RP were found to have a negligible effect. Okay, as a further refinement, we shall take the perturbed form of psi pp to be where mu, that's like a little u with a thing on it, where mu p, like lambda p, is a different constant for each wave function. The analysis is scarcely affected and yields the result lowercase h equals f squared sigma over p bracket 2 over 3 lambda p bracket parentheses r squared parentheses p plus mu p parentheses r3 parentheses p close bracket plus 1 over 2 lambda 2 over p bracket 1 plus 8 over 3 mu p parentheses r parentheses pp plus 2 mu 2 over p parentheses r squared parentheses pp close bracket. That's table 3.8, where parentheses r3 parentheses p equals parentheses lowercase r to the third parentheses pp dash sigma over squiggly o not equal to p bracket parentheses rx parentheses squiggly o p parentheses x parentheses p squiggly o plus parentheses r y parentheses squiggly o p parentheses y parentheses p squiggly o plus parentheses rz parentheses squiggly o p parentheses z parentheses p squiggly o close bracket, and parentheses capital R squared close parentheses p is the same as in table 3.4. The minimum value of lowercase h gives for the polarizability theta equals 4 over 9 sigma over p parentheses uppercase r squared close parentheses 2 over p parentheses 1 plus delta p close parentheses. That's table 3.9. 1 plus delta p equals 1 plus parentheses r to the third, close parentheses, 2 over p over 2 parentheses r squared, close parentheses, pp parentheses, capital R squared, close parentheses, 2 over p minus 4 over 3. No, wait. 4 parentheses r, close parentheses, pp parentheses, capital R to the third, close parentheses, p over 3 parentheses r squared parentheses pp parentheses capital R squared close parentheses p. So all that is over 1 minus 8 over not 8 parentheses r parentheses squared pp over 9 parentheses r squared parentheses pp. That's table 3.10. The quantity delta p, which may be regarded as a correction to the much simpler formula table 3.7, is shown in S4b to be important for the lighter atoms. 3a, evaluation of integrals. The functions parentheses r squared parentheses p and parentheses r to the third r cubed close parentheses p, which occur in formulae 3.5 and 3.7 and 3.10 for the atomic polarizability, can easily be evaluated once the electronic wave functions are known. We have defined parentheses capital R squared close parentheses p equals parentheses lowercase r squared close parentheses pp minus sigma over p not p. What does this mean? Sigma over p not equal to p bracket parentheses x parentheses pp parentheses x close parentheses pp plus parentheses y parentheses pp parentheses y parentheses pp plus parentheses z parentheses pp parentheses z parentheses pp close bracket, in which p, oh wait, these are, so there's a distinction between the pp's. The p and then p apostrophe, p with an apostrophe, are written shortly for the quantum numbers n, l, m, s, and n apostrophe, l apostrophe, m apostrophe, s apostrophe, respectively, and parentheses r squared parentheses pp equals violin whole psi asterisk over p r squared psi p dt parentheses x parentheses p apostrophe equals violin whole psi asterisk over p psi x psi p apostrophe dt, etc. Psi p is usually expressed in spherical polar coordinates in the form parentheses 2 pi parentheses minus 1 over 2 r parentheses nl line r parentheses p line over l m line parentheses cosine theta close parentheses e to the im phi times spin function, where r parentheses nl line r parentheses is the radial wave function normalized to unity, and p line over l m line parentheses cosine theta close parentheses the associated Legendre function. The angular and spin factors of parentheses r squared parentheses pp parentheses x parentheses pp parentheses y parentheses pp and parentheses z parentheses pp can be integrated at once, and incidentally parentheses z parentheses pp apostrophe, oh wait, some of those p's had parentheses z parentheses p apostrophe vanishes unless the quantum numbers of psi p and psi p apostrophe satisfy line l apostrophe dash l line equals 1, m apostrophe equals m, s apostrophe equals s. Likewise, parentheses x parentheses p apostrophe parentheses y parentheses pp apostrophe vanish unless line l apostrophe minus l line equals 1, line m apostrophe minus m line equals 1, s apostrophe equals s. The integration for r introduces integrals of the types parentheses r squared parentheses nl equals violin whole infinity 0 r squared bracket p of parentheses nl line r parentheses close bracket squared dt. Is that even a... Wait, that may not even be a t. What the fuck is that? Is that an r? Have I been saying t instead of r this whole time? dr. Parentheses r. Oh, it might be. Parentheses r parentheses nl n t equals violin whole infinity 0 rp parentheses nl line r parentheses p parentheses n apostrophe l apostrophe line r close parentheses dr, where p parentheses nl line r parentheses equals r, capital R parentheses nl line r close parentheses, and we find eventually that for an atom containing complete parentheses nl close parentheses subgroups parentheses capital R squared close parentheses nlms equals parentheses r squared lowercase r squared close parentheses nl minus 1 over 2 parentheses 2l plus 1 close parentheses squiggly o nl. That's table 3.11, where squiggly o nl is a function whose form depends upon the azimuthal quantum number L, but is independent of the magnetic and spin quantum numbers. Thus, for an atom containing s, p, d, and f shells, squiggly o no equals 2 sigma over n apostrophe parentheses r parentheses 2 over n 1 apostrophe 1 in... Oh, I don't know that. U squiggly o n1 equals 2 sigma over n apostrophe bracket parentheses r parentheses 2 over n apostrophe 0 n1 plus 2 parentheses r parentheses 2 over n 2 n1 close bracket squiggly o n2 equals 2 sigma over n apostrophe bracket 2 parentheses r parentheses 2 over n apostrophe 1 n2 plus 3 parentheses r parentheses 2 over n apostrophe 3 n2 close bracket squiggly o n3 equals 6 sigma over n apostrophe parentheses r parentheses 2 over n apostrophe 2 n3, and that's table 3.12. The range of n apostrophe in these sums depend upon the value of L apostrophe either 0, 1, 2, or 3. Associated with n apostrophe, but it includes every occupied subgroup having the quantum numbers n apostrophe, L apostrophe. The terms parentheses capital R to the third close parentheses p are treated similarly, and we find parentheses capital R to the third close parentheses NLMS equals parentheses lowercase r to the third close parentheses NL minus 1 over 2 parentheses 2L plus 1 close parentheses TNL. That's table 3.13, where TNL is simply related to squiggly ONL, as it is only necessary to replace parentheses R parentheses 2 over NT and 2 over NTNL, where it occurs in squiggly ONL by the product parentheses R squared parentheses NTNL parentheses R parentheses NTNL. For example, TN1 equals 2 sigma over n apostrophe bracket parentheses R squared parentheses n apostrophe 0 in 1 parentheses R parentheses n apostrophe 0 in 1 plus 2 parentheses R squared parentheses 2 parentheses R squared parentheses n apostrophe 2 in 1 parentheses R parentheses n apostrophe 2 in 1 close bracket. When the atom contains incomplete subgroups, it is necessary first to consider whether the electronic configuration is degenerate, and if so, whether the previous argument needs to be modified. However, if an S shell is incomplete, as in the alkali atoms, no modification is required other than the contribution of that shell to the squiggly O and R terms. Wait, I can't tell. No, that's a T. Squiggly O and T terms, as defined by table 3.12, shall be halved. The self-consistent atomic fields calculated by Hartree and others provide suitable functions, capital P, parentheses NL line R, parentheses from which to evaluate, parentheses R squared, parentheses NL, NL, parentheses R, parentheses NT, NL, etc., by numerical integration, and we can therefore calculate the polarizability of any atom or ion for which the self-consistent field is known, provided proper care is taken when there is an incomplete subgroup. It is true that the Hartree functions for the same L but different N are not exactly orthogonal. But the error is found to be too small to make it necessary to derive an orthogonal set. A more important disadvantage is that they neglect electron exchange entirely, and although the self-consistent field equations have been modified by Fock to include exchange, Fock waves have as yet been calculated for very few atoms. A comparison of Hartree and Fock functions is made below. 3b, numerical results and discussion. In SS3, 3 different expressions for the polarizability of an atom were obtained by progressive application of the variation method. We shall now discuss the following points which arise in comparing the polarizabilities calculated from these formulae with each other and with experimental values. The effect of exchange on the calculated polarizabilities, the effect of introducing exchange in the electronic wave functions, the effect of the more accurate variation function leading to table 3.9, and Kirkwood's relation between polarizability and magnetic susceptibility. These points will be illustrated with the help of available wave functions for atoms and ions with complete subgroups. It was shown above that the functions parentheses capital R squared close parentheses P occurring in tables 3.5 and 3.7 depend only on the quantum numbers N and L, and hence the summation within each parentheses N, L, parentheses subgroup can be carried out at once. If this is done in table 3.11 substituted for parentheses capital R squared parentheses P, then tables 3.5 and 3.7 rewritten in CGS units are respectively theta equals 4a 3 over 0 over 9n bracket sigma over nl bracket VL parentheses R squared close parentheses NL minus squiggly O NL bracket squared. 1. Number 2 is theta equals 4a 3 over O over 9 sigma over NL 1 over VL bracket VL parentheses R squared parentheses NL minus squiggly O NL close bracket squared, where AO is the radius of the first Bohr orbit in the hydrogen atom, parentheses 4a 3 over O slash 9 equals 0.654 times 10 to the negative 25th centimeter cubed. The terms parentheses R squared parentheses NL and squiggly O NL are still expressed in atomic units. The summations are for all occupied subgroups, and VL equals 2 parentheses 2L plus 1 parentheses. Of these results, number 1 was derived from one parameter only and should be compared with that found by Kirkwood using for the atomic wave function the simple product psi equals psi theta 1 psi b2 ... psi vn, which takes no account of the electron exchange. Likewise, with number 2, we may compare the results obtained by Hellman, also neglecting exchange, but using a different parameter for each subgroup of electrons. The formulae of Kirkwood and Hellman, which we will denote by 1a and 2a respectively, are theta equals 4a 3 over 0 over 9n bracket sigma over NL VL parentheses R squared parentheses NL bracket squared, and 2a is theta equals 4a 3 over 0 over 9 sigma over NL VL parentheses R squared parentheses squared over NL. In the same units and notation, it will be seen that the only difference is in the absence of the term squiggly O in L. These four expressions for theta exemplify two general principles. First, that the inclusion of electron exchange, which is similar to the removal of a constraint on the system, decreases the energy of perturbation and therefore the polarizability. Thus, the values obtained from 1 and 2 are respectively less than those obtained from 1A and 2A, since squiggly-O NL is always positive. Secondly, it is generally true in applications of the variation method with a given form for the perturbed wave function that, as more parameters are introduced, the calculated energy approaches the exact value as a lower limit. The energy of polarization being negative, we should expect the calculated polarizability to increase in magnitude as the number of parameters is increased. And in fact, the values given by 2 and 2A are respectively greater than those given by 1 and 1A. To illustrate these remarks, the known Hartree, there's a footnote here, I am indebted to Dr. J. McDougall for the use of unpublished wave functions for NE. Other Hartree fields have been used as follows. A field calculated by J. McDougall and R.A. Buckingham, CS plus and also K plus from D.R. Hartree, 1934, RB plus analytical wave functions derived from the Hartree function by J.C. Slater, 1932. The known Hartree fields of NEA, RB plus, and CS plus have been applied as suggested in SS3A to calculate values of theta, which are shown in Table 1. Table 1, calculated atomic polarizabilities, theta times 10 to the 24 method. 1 with exchange, 1A without exchange, bracket 1 parameter, NE, 0.348 with exchange, 0.348 with exchange, 0.774 without exchange. A, 1.49 with exchange, 3.38 without exchange. RB plus, 1.09 with exchange, 2.54 without exchange. CS plus, 1.43 with exchange, 4.32 without exchange. 2 with exchange, 2A without exchange. Parameter for each subgroup. NE 0.517 with exchange, 0.969 without exchange. A 4.09 with exchange, 7.16 without exchange. RB plus 4.35 with exchange, 7.47 without exchange. CS plus 8.44 with exchange, 16.9 without exchange. Table 1 shows that the inclusion of exchange terms in the formula for theta may reduce the calculated value by as much as 50%. Before making any comparison with experiment, we must also consider the effect of exchange on the electron wave functions as shown by the difference between Hartree and Fock functions. The few Fock functions which are known indicate the change to be expected. Thus, Dr. and W. Hartree, 1935. Oh, here's a footnote. The Fock field for Na plus was calculated by V. Fock and M. Petrushin, 1934. I'm indebted to Professor Hartree for information about the Fock field of Cl minus before it was published. Hartree, Dr. and W. 1936. Dr. and W. Hartree, 1935. I've already pointed out that in normal, B, the term parentheses R squared parentheses 2020 is about 12% less, and in Na plus parentheses R squared parentheses 2121 is about 13% less for the Fock field than for the Hartree field. In Cl minus, the decrease in parentheses R squared parentheses 3131 is as much as 30%. The effect of exchange on the squiggly-O NL terms can be examined in Na plus, Cl minus, and it is found that these terms are practically the same for the Fock and Hartree fields. The corresponding values of theta, 10 to the 24, calculated from table 2, are as follows. Be Hartree 12.0, Fock 9.28, Na plus Hartree 0.183, Fock 0.134, Cl minus 16.2, Hartree 16.2, Fock 6.9. The use of Fock functions thus leads to a further decrease in the calculated polarizabilities and therefore to better agreement with experiment, since Hartree functions are found to give values which are too high. There is, however, one important exception to this general statement. The Hartree field for Na plus gives theta equals 0.183 times 10 to the negative 24, which is slightly larger than 0.17 times 10 to the negative 24, deduced by Mayer in 1933 from spectroscopic data, but less than 0.245 times 10 to the negative 24 given by Hadeweiler's 1925 measurements of the refractivities of alkali halides in solution. We are therefore led to consider the more accurate formula, equation 3.9, which when written in CGS units is theta equals 4a 3 over 0 over 9 sigma over NL 1 over VL bracket VL parentheses R squared parentheses NL minus squigglio NL close bracket square parentheses 1 plus delta NL close parentheses. That's number 3. Table 3. This represents the closest approximation to the actual atomic system which has been considered, as the assumed system satisfies the Pauli principle and allows 2 independent parameters for each subgroup. The difficulty in applying it arises from the calculation of delta NL, terms for which accurate wave functions are necessary. Nevertheless, the available functions indicate the relative importance of these terms in different atoms. In Table 2 are given the values 1 plus delta NL, those in the first column being derived by numerical integration from self-consistent functions. Hartree functions, with the exception of BE and Na+, for which Fock functions were used. And those in the second column from analytical functions, Slater 1930, of the type R to the N asterisk minus 1 exp parentheses dash N asterisk R slash Z minus S close parentheses, in which N to the asterisk is an effective quantum number and S a screening constant, since the inner groups of electrons make a very small contribution to theta. Only the outer group in each atom has been considered, although a calculation for Na plus shows that the contribution of an inner S group may be doubled. The large discrepancy between the two values for the 2p group of neon may be understood by comparing the theoretical values of the magnetic susceptibility X given by the same wave functions. Thus, the Slater function underestimates the extension of the 2p charge distribution from the nucleus and gives a susceptibility less than that observed, whereas the Hartree function does the opposite. Hence, the proper value of 1 plus delta parentheses 2p parentheses probably lies between those given. For Na+, however, both the Slater and Fock functions, here's a footnote. The Slater and Fock functions given x equals negative 4.17, 5.0 times 10 to the negative 6 respectively. The experimental value for ions in solution is about negative 5.7 times 10 to the negative 6, and for crystal ions about negative 6.1 times 10 to the negative 6. Oh. Yeah, now I lost my place. Where was that? Damn it, where was the footnote? Oh, okay. For Na+, however, both the Slater and Fock functions appear to underestimate x, so that the correct value of 1 plus delta 2p parentheses 2p parentheses may be greater than 1.15. But the general conclusion is that the value of 1 plus delta NL for an outer group differs appreciably from unity only for the lighter atoms such as helium, neon. Oh, okay, so these are periodic. I've been saying, okay, helium, neon, and sodium plus. So I guess it's like a sodium ion. Its effect is then to increase the calculated polarizability, and for sodium ion, the agreement with experiment is thereby slightly improved. Table 2, helium 1 plus delta, parentheses 1s, parentheses self-consistent functions, dash. Okay, wait, no, this is a table. Okay, self-consistent functions, Slater, helium 1 plus delta, parentheses 1s, parentheses, no self-consistent functions, it looks like Slater 1.125, BE, I forget which element that is, 1 plus delta, parentheses 2s, parentheses 1.00, self-consistent functions, Slater 1.01, NE 1 plus delta parentheses 2p parentheses 1.40 self-consistent functions Slater 1.03. A 1 plus delta parentheses 3p parentheses 1.005 self-consistent functions Slater 1.00. KR, I think it's Krypton, 1 plus delta parentheses 4p parentheses no self-consistent functions Slater 1.005. XE, I think was it Xeon, 1 plus delta parentheses 5p parentheses no self-consistent functions Slater 1.01. Sodium ion bracket 1 plus delta parentheses 2s parentheses 1 plus delta parentheses 2p parentheses self-consistent functions 2.03 and 1.15 Slater 2.83 and 1.03. K plus, I don't know, okay, I don't know, 1 plus delta parentheses 3p parentheses self-consistent functions 1.03 Slater 1.00. It is perhaps worth mentioning an empirical method of estimating these correction terms. It was pointed out by Kirkwood that polarizability and magnetic susceptibility are related quantities, and using his result for theta, formula 1a, he suggested the relation minus x equals LE squared A 1 over 2 over 0 over 4mc squared to the square root of n theta. Further developments by the variation method show that this is hardly justified, though as an empirical relation it is more successful than one would expect, Brindley 1933. However, we may make use of the result that the main part of theta comes from an outer group of electrons, say V0, in number. Then, if parentheses r squared parentheses 0 and squiggly o 0 are the values of parentheses r squared parentheses nl and squiggly o nl for this group, its contribution to x is x0 equals minus LE squared A 2 over 0 over 6mc squared V0 parentheses r squared parentheses 0. That's equation 3.14. By comparing 3.14 and table 3, we find that approximately bracket 9v0 theta over 4a3 over 0 parentheses 1 plus delta apostrophe over 0 close bracket to the 1/2 plus squiggly o 0 equals minus 6mc squared over LE squared A2 over 0 x0. That's table 3.15, equation 3.15. Now, suppose theta and x are known experimentally, and that x0 can be estimated from x, as when the relative importance of the different electron groups is known from the self-consistent field. If, in addition, squiggly O0, which is usually much smaller than the other terms, is given its theoretical value, then the relation equation 3.15 can be applied to find 1 plus delta apostrophe over 0. The results in table 3 have been derived this way. Table 3. Oh, here's a footnote. For the rare gases, the experimental values of theta are taken from C and M Cuthbertson, 1911, and of X from Mann, 1936. The data for the ions refer to ions in the crystalline state. The values of X are those given by Brindley and Hoare, 1935, and the values of theta are derived from the refractivities of the alkali halide crystals measured by Spangenberg, 1923. Okay, so this is table 3. Theta times 10 to the 24. Negative theta times 10 to the 24. Negative x times 10 to the 6. Negative x0 times 10 to the 6th. Squiggly O 0. 1 plus delta apostrophe 0. Okay, NE for... So NE, and this is for theta times 10 to the 24, is 0.392. Na plus for theta times 10 to the 24 is 0.280. Cl minus for theta times 10 to the 24 is 3.01. A for theta times 10 to the 24 is 1.63. K plus for theta times 10 to the 24 is 1.09. Kr for theta times 10 to the 24th is 2.465, little 5 there in the corner, whatever that means. Cs plus for theta times 10 to the 24 is 2.72. Ne for negative x times 10 to the 6th is 6.75. Na plus for negative x times 10 to the 6 is 6.1. Cl minus for negative x times 10 to the 6 is 24.2. A for negative x times 10 to the 6 is 19.54. K plus for negative x times 10 to the 6 is 14.6. Kr for negative x times 10 to the 6 is 28.0. Cs plus for negative x times 10 to the 6 is 35.1. Ne for negative x 0 times 10 to the 6 is 5.37. Na plus for negative x 0 times 10 to the 6 is 4.56. Cl minus for negative x 0 times 10 to the 6th is 18.9. A for negative x 0 times 10 to the 6th is 14.7. K plus for negative x 0 times 10 to the 6th is 10.7. Kr for negative x 0 times 10 to the 6th is 17.4. Cs plus for negative x 0 times 10 to the 6th is 19.3. Ne for squigglio 0 is 1.7. Na plus for squigglio 0 is 1.23. Cl minus for squigglio 0 is 5.74. A for squigglio 0 is 4.77. K plus for squigglio 0 is 3.67. Kr for squigglio 0 is 6.5. Here's a footnote. The value of squigglio 0 for Kr is calculated from an approximate self-consistent wave function for the 4s and 4p electrons, kindly sent to me by Professor D.R. Hartree. CS plus for squiggly 0 is 8.37. Ne for 1 plus delta apostrophe over 0, 1.43. Na plus for 1 plus delta apostrophe over 0 to 1 plus delta apostrophe, and then there's a little 0 in the right hand corner. Na plus is 1.23. Cl minus for that equation is 0.84. A for 1 plus delta apostrophe 0 in the corner is 0.79. K plus for 1 plus delta apostrophe 0 is 1.03. Kr for 1 plus delta apostrophe 0 is 0.95. Cs plus for 1 plus delta apostrophe 0 is 0.96. Direct comparison of the values of 1 plus delta apostrophe 0 with the theoretical values 1 plus delta 0 is hardly justified, since the error of approximation involved in equation 3.15 is not known. Further errors may be introduced by inaccuracy in the wave functions affecting squigglio 0 and the ratio x0/x, and in the experimental data, which for the ions are especially uncertain. But although the values in Table 3 must be accepted with caution, they do confirm the theoretical result that the delta terms are important for the lighter atoms Ne and Na+. It is, however, rather surprising that the delta apostrophe 0 value for argon should be so large and negative. Appendix. Much of the integration required in SS3 is applicable to other problems, and so we shall give a separate account of the methods used, beginning with the integrals, such as those in equation 3.2, which contain the density function psi asterisk psi. This is replaced by the determinant A, obtained by multiplication of the determinant psi asterisk and psi, defined by equation 3.1. A has the form A equals matrix A11, A12, A1n, A21, A22, A2n, AN1, AN2, ANN closed matrix, where A PQ equals sigma over P psi asterisk over PP psi PQ. The summation, including all occupied states from theta to V in A, has the property that it can easily be integrated over the coordinate space of any electron. See Leonard-Jones 1930b. For instance, if F parentheses P parentheses is a function of the coordinates of the pth electron only, then by completing the integration for all electrons except the pth, it is easily proved that 1 over n exclamation point violin hole psi asterisk F parentheses P parentheses psi dr equals 1 over n violin hole F parentheses P parentheses APP drp. Nope, that's a T. Those were T. The way they write the R's and T's. Okay. Okay, so the equation is supposed to be 1 over n exclamation point violin hole psi asterisk f parentheses p parentheses psi dt equals 1 over n violin hole f parentheses p parentheses app dtp, a result which is independent of the choice p. We can therefore drop the electron suffix and remove the factor 1/n by summing for p from 1 to n. Thus, 1 over n exclamation point sigma over p violin hole psi asterisk f parentheses p parentheses psi dt equals sigma over p violin hole psi asterisk over p f psi p dt. Similarly, if g parentheses p close parentheses g apostrophe parentheses q close parentheses are respectively functions of the coordinates of the pth and kth electrons only, then by integrating for all electrons except the pth and kth, 1 over n exclamation point violin hole psi asterisk g parentheses p close parentheses g apostrophe parentheses q close parentheses psi dt equals 1 over n parentheses n minus 1 parentheses violin hole g parentheses p close parentheses g apostrophe parentheses q close parentheses matrix APP AQP close matrix DTQ equals 1 over n parentheses n minus 1 close parentheses sigma over p sigma over squiggly o violin hole g parentheses p close parentheses g apostrophe parentheses q close parentheses bracket psi asterisk over pp psi asterisk over squiggly o q psi squiggly o q minus psi asterisk over pp psi pq psi asterisk over squiggly o q psi squiggly o p close bracket dtq. This is likewise independent of the choice p and q, hence dropping the electron suffixes 1 over n exclamation point sigma over p sigma over q not equal to p violin hole psi asterisk g parentheses p close parentheses g apostrophe parentheses q close parentheses psi dt equals sigma over p sigma over squiggly o bracket violin hole psi asterisk over p g psi p dt violin hole psi asterisk over squiggly o g apostrophe psi squiggly o dt apostrophe minus violin hole psi asterisk over pg psi squiggly o dr violin hole psi asterisk over squiggly o g apostrophe psi p dr apostrophe close bracket. Turning now to equation 3.2, we require the integral of v squared where v equals negative sigma over p parentheses rp dot f close parentheses v squared may be written sigma over p bracket parentheses rp dot f parentheses squared plus sigma over q not equal to p parentheses rp dot f close parentheses rq dot f close parentheses close bracket. And so from 2 and 3 we get at once 1 over n exclamation point violin hole psi asterisk v squared psi dt equals sigma over p bracket violin hole parentheses r dot f close parentheses squared psi asterisk over p psi p dt plus sigma squiggly o not equal to p bracket violin hole parentheses r dot f close parentheses psi asterisk over p psi p dt violin hole parentheses r asterisk dot f close parentheses psi asterisk over squiggly o psi squiggly o dt apostrophe minus violin hole parentheses r dot f parentheses close parentheses psi asterisk over p psi squiggly o dt violin hole parentheses r apostrophe dot f close parentheses psi asterisk over squiggly o psi p d apostrophe t close bracket close bracket. Let us introduce a system of rectangular axes in which r has direction cosines L, M, N, and F has direction cosines sigma, b. Oh god, some Greek. Looks like a y. It's not a y. It's not a lambda. I don't know. Sigma b Greek y, whatever that is. Sigma b y. Then if r, f are the magnitudes of r and f, violin hole psi asterisk over p parentheses r dot f parentheses squared psi b dt equals f squared violin hole psi asterisk over p r squared parentheses L theta plus MB plus N Greek y, close parentheses, squared psi p dt. And when we average for all values of LMN, i.e. for all orientations of the atom relative to the direction of f, this integral reduces to 1 over 3f squared parentheses r squared parentheses pp. Now, parentheses r dot f parentheses is an odd function of r, and so its average value with respect to the charge density psi asterisk over p psi p is 0. The second term in 4 therefore vanishes. The remaining integrals can be treated like the first, and finally 1 over n exclamation point violin whole psi asterisk v squared psi dt equals 1 over 3f squared psi sigma over p bracket parentheses r squared parentheses pp minus sigma over squiggly o not equal to p bracket parentheses x parentheses squiggly o p parentheses x parentheses p squiggly o plus parentheses y parentheses squiggly o p parentheses y parentheses p squiggly o plus parentheses z parentheses squiggly o p parentheses z parentheses p squiggly o close bracket close bracket. We also require the integral of parentheses grad p v squared close parentheses, in which grad p to the v equals negative grad p parentheses r p dot f. From 2, it follows that 1 over n exclamation point sigma over p violin whole psi asterisk parentheses grad p to the v parentheses squared psi dt equals sigma over p violin whole psi asterisk over p bracket grad parentheses r dot f parentheses bracket squared psi p dt. And the right hand side is easily shown to be equal to n. These results lead to at once to equation 3.4. When it is necessary to use equation 2.5 for the perturbation energy, rather more complicated integrals occur, but they can be reduced in essentially the same way. Instead of the charge density psi asterisk psi, we usually have psi asterisk over pq d asterisk over pq dpp psi pp, in which dpp is the first minor of psi pp in the determinant psi dot d asterisk over pq, and dpp are therefore determinants with parentheses n minus 1 parentheses rows and columns, and their product is likewise a determinant parentheses n minus 1 rows and columns, having the form d asterisk over pq dpp equals parentheses minus parentheses to the p plus q matrix a apostrophe 11 dot 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 a apostrophe 1 p minus 1 a apostrophe 1 p plus 1 dot 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 a apostrophe 1 n, and then go down 6 dots a apostrophe q minus 1 1 a apostrophe q plus 1 1, down 6 dots a apostrophe n 1 over 6 dots a apostrophe np minus 1 a apostrophe np plus 1 over 6 dots a apostrophe nn, and then up 6 dots a apostrophe q plus 1 n a apostrophe q minus 1 n, close matrix, where a apostrophe pq equals sigma over squiggly o not equal to p psi asterisk over squiggly o p psi squiggly o q. The summation including all states from theta to v except p. The product of this determinant with psi asterisk over pq psi pq is like 1, easily integrated over the coordinate space of any electron, and we obtain the following useful results: sigma over p violin whole psi asterisk pq d asterisk pq dpp psi pp f parentheses p parentheses dt equals 0 when q is not equal to p, equals n exclamation point violin whole psi asterisk over p f psi p dt when q equals p, sigma over p sigma q not equal to v violin whole psi asterisk pq d asterisk pq dpp psi pp g parentheses p parentheses g apostrophe parentheses t parentheses dt equals 0 when t is not equal to q, equals n exclamation point sigma over squiggly o not equal to p bracket violin whole psi asterisk over pg psi p dt violin whole psi asterisk over squiggly o g apostrophe psi squiggly O dt apostrophe minus violin hole psi asterisk over pg psi squiggly O dt violin hole psi asterisk over squiggly O g apostrophe psi p dt apostrophe close bracket when t equals q. Integrals, which involve psi asterisk pq d asterisk over pq d squiggly O p psi squiggly O p parentheses squiggly O not equal to p, can also be reduced by the same method. We find that violin hole psi asterisk over pp d asterisk over pp d squiggly O p psi squiggly O p dt equals 0. Violin hole psi asterisk over pq d asterisk over pq d squiggly O p psi squiggly O p f of parentheses p parentheses dt equals 0. Violin hole psi asterisk over pq d asterisk over pq d squiggly O p psi squiggly O p g parentheses p parentheses g apostrophe parentheses q parentheses dt equals 0. Let us and that's the fifth equation for the appendices. Let us now consider the integral of psi asterisk v phi, where v equals sigma over p vp is above, and phi equals sigma over p lambda p sigma over p psi pp dpp vp. We write psi asterisk v phi equals psi asterisk parentheses sigma over lv t parentheses sigma over p lambda p sigma over p psi pp dpp vp, in which the coefficient of lambda p is psi asterisk sigma over p psi pp dpp vp parentheses sigma over t vt close parentheses. If psi asterisk in this expression is replaced by its expansion in terms of the elements of the pth row, i.e. by sigma over q psi asterisk over pq d asterisk over pq, then psi asterisk v phi equals sigma over p lambda p bracket sigma over p sigma over q psi asterisk over pq d asterisk pq dpp psi pp parentheses v2 over p plus sigma over t is not equal to p vp vt close parentheses close bracket. When we apply equations 4 and insert vp equals negative parentheses rp dot f, the terms which do not vanish on integration give 1 over n exclamation point violin hole psi asterisk v phi dt equals psi over p lambda p bracket violin hole psi asterisk over p parentheses r dot f parentheses squared psi p dt minus sigma squiggly O not equal to p violin hole psi asterisk over p parentheses r dot f parentheses psi squiggly O dt per violin hole. Man, I'm still not sure if that's a T or an R. I've been switch DR or DT. The way they're writing them is so difficult to read. DR, DT, D. Anyway, violin hole psi asterisk over squiggly O parentheses R apostrophe dot F close parentheses psi b dr apostrophe bracket, which by our previous results equals 1 over 3f squared sigma over p lambda p parentheses r squared close parentheses p. From equation 2.5, we have also the following term involving grad p violin hole grad p phi asterisk grad p phi dr minus 1 over n exclamation point violin hole phi asterisk phi dr violin hole grad p psi asterisk grad p psi dr, since phi equals sigma over p lambda p sigma over p lambda p, or sigma over p psi pp dpp vp, and dpp contains the coordinates of all electrons except the pth. Grad p phi equals sigma over p lambda p bracket dpp parentheses psi pp grad pvp plus vp grad p psi pp close parentheses plus sigma over q not equal to p psi pq vq grad p dpq close bracket. On integration, we neglect all terms except that in parentheses grad p vp parentheses squared, assuming that the remainder, which with the integral of grad p psi asterisk grad p psi are analogous to equation 2.6 are small, approximately therefore 1 over n exclamation point sigma over p bracket violin hole grad p phi asterisk dot grad p phi dr minus 1 over n exclamation point violin hole phi asterisk phi dr violin hole grad p psi asterisk dot grad p psi dr close bracket equals 1 over n exclamation point sigma over p violin hole sigma over p lambda p d asterisk over pp psi asterisk over pp bracket sigma over squiggly-o lambda squiggly-o d squiggly-o p psi squiggly-o p close bracket grad parentheses grad pvp close parentheses squared dr equals 1n exclamation point sigma over p lambda 2 over p violin hole psi asterisk over pp d asterisk pp dpp psi pp parentheses grad pvp parentheses squared dr by equation 5 equals psi equals sigma over p lambda 2p violin hole psi asterisk over p bracket grad parentheses r dot f close bracket squared psi p dr by 4 equals f squared sigma over p lambda to the 2 over p. Equation 3.6 for the energy of polarization follows at once from these results. The integrals which arise when we introduce the more accurate perturbed functions described in SS3 do not require any extension of the method outlined above, and we shall therefore not give further details. I am very grateful to Professor J.E. Leonard Jones, FRS, for many helpful discussions, also to the Department of Scientific and Industrial Research for a grant during a period when many of these calculations were made. Summary: the theory of the polarization of an atom by a uniform electric field is developed using a variation method introduced by Kirkwood in the atomic polarizabilities of several atoms containing closed electron groups calculated from their self-consistent fields. It is verified that an anti-symmetrical wave function for the atom gives better results than a symmetrical function. Higher approximations in which more parameters are introduced in the perturbed wave functions are considered. Calculations with the Fock fields of the atoms Be, Na+, and Cl- show that the inclusion of exchange in the electron wave functions has considerable effect on the calculated polarizabilities. References: Atanesov, 1930, Physics Rev. 361232. Alright, we ain't gotta read all that. The Quantum Theory of Atomic Polarization 2, The Van der Waals Energy of Two Atoms by R.A. Buckingham, B.A., Queen's University, Belfast, communicated by J.E. Leonard Jones, FRS, received 29 December 1936. In a previous paper, page 94, which will be referred to as paper 1, the polarizability of an atom in a uniform electric field was calculated by a method of varying parameters. The same method can equally well be applied to find the energy of interaction of two atoms a large distance apart by treating their interaction as a perturbation of the system in which the atoms are separated by an infinite distance. The mutual energy other than that arising from the ionic charges, if they exist, of the atoms is usually called the van der Waals energy. We shall suppose that one atom contains N1 electrons and is represented in its unperturbed state by a determinantal wave function psi1 as in equation 3.1 of paper 1, containing electronic functions of the type psi p1p apostrophe, where p1 may be any one of the n1 occupied states, theta 1 b1 ... v1 of this atom, and p denotes that the spatial and spin coordinates of the pth electron are inserted in psi p1p p1p. Similarly, the second atom contains N2 electrons and is represented in its unperturbed state by a determinant psi2 containing function psi p2r, where p2 may be one of the N2 occupied states, theta 2 b2 ... v2, and r refers to the coordinates of the rth electron. Then, if we neglect any exchange of electrons between the atoms, the wave function of the unperturbed system of two atoms is psi equals psi 1 psi 2, and violin whole psi asterisk psi dr equals n1 exclamation point n2 exclamation point. Okay, that's the end. I'll find the rest of part 2 later. That's a little teaser for the second paper on that one. Okay, that brings us to today. Discoverers of colorful quantum dot nanotech win 2023 Nobel Prize in Chemistry. Quantum dots can be found in modern computers, televisions, LED lights, and more. By Laura Theseus. Published October 4th, 2023, 9 a.m. Eastern Dick Time, EDT. The 2023 Nobel Prize in Chemistry was jointly awarded to Maungi Bawendi, Louis Bruce, and Alexei Ekimov for the discovery and developments of quantum dots. These nanoparticles are so small that their size determines their properties. Quantum dots can be found in modern computers, televisions, and LED lights, among numerous applications. Bawendi is a professor at the Massachusetts Institute of Technology. Bruce is a professor emeritus at Columbia University, and Ekimov works for a company called Nanocrystals Technology in New York State. Quote, for a long time, nobody thought you could ever actually make such small particles, Johann Akvist, chair of the Nobel Committee for Chemistry, said during a news conference. But this year's laureates succeeded. Size matters in the nanoscale. Quantum dots are among the smallest components of nanotechnology. Typically, an element's properties are governed by how many electrons it has. When that matter shrinks down to nano dimensions, quantum phenomena arise. This means the element's properties are now governed by the size of the matter instead of the number of electrons it has. Quantum dots are made of only 1,000 atoms. By comparison, one quantum dot is to a soccer ball as a soccer ball is to the planet Earth. A quantum dot is a crystal that often consists of just a few thousand atoms. In terms of size, has the same relationship to a football as a football has the size of Earth. Oh, there's a nice little chart here with pictures. The quantum dots that Bawendi, Bruce, and Ekimov produced are particles small enough for their properties to be determined by quantum phenomena. They are among the smallest but most important particles, nanotechnology. Quote, quantum dots have many fascinating and unusual properties. Importantly, they have different colors depending on their size, Akvist said in the statement. The movement of electrons in quantum dots is highly constrained. This then affects how they absorb and release visible light, allowing for very bright colors. The quantum dots themselves are nanoparticles that glow red, blue, or green, and the color depends on the size of the particles. Larger dots shine red and smaller dots shine blue. The change in color depends on how electrons act differently in more confined or less confined spaces. Quantum effects arise when particles shrink. When particles are just a few nanometers in diameter, the space available to electrons shrinks. This affects the particle's optical properties. And then there's a chart here, electron wave. At the left side of the chart, larger nanoparticle, more space for the electron wave. As it gets smaller nanoparticle, less space for the electron wave. Quantum dots absorb light and then emit it at another wavelength. Its color depends on the size of the particle. Big discoveries, super small particles. In 1937, physicists theorized that size-dependent quantum effects could arise in nanoparticles. However, it was almost impossible to sculpt in nano dimensions, so few believed that it was possible. So yeah, the 1937 study is what I read before this. And that was... where'd it go? That was a study from Queen's University, Belfast. Yeah, that's where the study was. During the early 1980s, Ekimov created size-dependent quantum effects in colored glass. The color of the glass came from the nanoparticles of copper chloride. With this colorful experiment, Ekimov demonstrated that the particle size affected the color of the glass via quantum effects. A few years later, Bruce became the first scientist in the world to prove that size-dependent quantum effects in particles were floating freely in a fluid. Bruce and Ekimov were actually working independently from one another when they made their initial discoveries. In 1993, Bowendi revolutionized the chemical production of quantum dots. His techniques resulted in almost perfect particles, which was necessary for using the quantum dots in a wide range of applications. Quantum dots can now be found in computer monitors and television screens, and even help biochemists and surgeons map tissues and remove tumors. Last year's chemistry prize was also awarded to a trio of chemists: Carolyn R. Bertozzi for work in bioorthogonal chemistry, alongside Kayberry Sharpless and Morton Meldal for laying the foundation for click chemistry. So that's, yeah, quantum dots.
比尔是科学家，
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 科学定律，
比尔是科学家，
惯性是物质的性质之一。
比尔
是科学家，
倒数7秒，计时开始。
比尔是科学家。